All right, so this is 11.10. This is the second to last section that we cover in this class, and it's possibly the longest section that we cover as well. There's a lot of material to get through here. So we're talking about Taylor and Maclaurin series, which is sort of a jumping off point, or which 11.9 is sort of a jumping off point for. 11.9, we talked about how you can represent functions by power series. And we showed how to do that with a few functions using some substitutions and some clever techniques. In this section, we're talking about a more straightforward way, I guess, of finding the power series representation for a function. So let's go ahead and talk about where this comes from, and then we'll start looking at some examples. Let's suppose that you have a function f of x that can be represented by a power series like this. Notice that this is a power series centered at some number a, and we're being general about what the coefficients are, c0, c1, c2, c3, and so on and so forth. Our goal here is to figure out if there's a way to deduce what these coefficients are, because if we can figure out what those coefficients are, then we'll have a specific power series for a given function. Let's suppose also that the series converges on some interval centered at a with a positive radius of convergence. So this means that we're looking at an interval of convergence as opposed to just a single number a on which this converges. From the previous section, we know that you can differentiate power series term by term. And so we're going to do that. We're going to look at what would happen if we took the derivative of this thing multiple times. So if I find f prime of x, for example, my constant term c0 is going to go away. c1 will be my new constant term, and then I'm using the power rule on all of these other terms here. So the 2 comes down, gives me 2c2 times x minus a, and the 3 comes down here, 3c3 times x minus a squared, and so on and so forth. We also know from that theorem in the previous section that the new power series that we get from differentiating f of x up here will have the same radius of convergence. And just by repeating this over and over again, we can continue differentiating this power series, and on each new power series we obtain here, we'll continually have the same radius of convergence. So that's a convenient little fact. So continuing on in this way, if I do f double prime of x, now my c1, the constant from this power series, will go away, and 2 times c2 is going to be my new constant term. And then continuing on by applying the power rule to all of these other terms, the 2 comes down, and I get 3 times 2 times c3 here. This 3 comes down here, I'm going to get 4 times 3 times c4 here, times x minus a squared, of course. And then I'm intentionally not doing the multiplication here. I'm not doing 3 times 2 is 6, and I'm not showing that 4 times 3 is 12, because if I leave these as products, I'm going to start to notice a pattern that I really want to take advantage of. So let's look at a couple more derivatives from there. F triple prime. This constant term is going to go away. 3 times 2 times c3 will be my new constant term, and then over here, this 2 is going to come down. I'm going to get 4 times 3 times 2 times c4, x minus a, and then you can kind of see how this pattern continues. So if you notice what's happening, the more and more times that I differentiate this power series, the more factors end up in these products in front of these constant terms. And not only that, those factors are starting at some number, and or the products, I should say. Those products start at some positive integer, and then I multiply all of the positive integers that are less than that. So 4 times 3 times 2 here, 5 times 4 times 3. In the next differentiation step, I'm going to get a 2 that comes out of there. So 5 times 4 times 3 times 2. By the time these things get to the constant term here, once we've differentiated enough times for that guy to come down to this constant term, what we have is a factorial. So for example, 4 times 3 times 2 is the same thing as 4 factorial. Yes, normally we think of 4 factorial as 4 times 3 times 2 times 1, but multiplying by 1 doesn't actually change it. So you don't need the times 1 there. This is just 4 factorial. The next thing I want to do is in my function, as well as each one of these derivatives that I just took, I want to plug a in. And the point of that is that when you plug a into a power series that's centered at a, all of these terms will go to 0, and you're left with just that. I'm pointing off screen. All of these terms will go to 0, and that constant term is going to be the only thing that's left. So for example, if I plug 0 into f of 0 would just be c naught, which is right here, c naught. C naught is the same thing as 0 factorial times c naught. And as a reminder, 0 factorial is defined to be the same thing as the number 1. This is a fact that you should already know, but if you didn't know that, 0 factorial is not actually 0. It's equal to 1. And there are plenty of good reasons for defining it this way, but we just need to remember that. So c naught is the same thing as c factorial times c naught. This may seem like an odd thing to put here, but it's because there's going to be a pattern that arises. If I go up to f prime now, this power series that I found, if I plug a into this power series, then the constant term c1 is the only thing that's going to be left. So that f prime of a is equal to c1. Or I can alternatively write that as 1 factorial times c1, because 1 factorial is also equal to 1. So I can continue doing that. If I plug a into f double prime, then 2 times c2 is going to be my term that's left, which is the same thing as 2 factorial times c2. If I plug an a into f triple prime, I get 3 times 2 c1 or c3, which is c3 factorial. I'm missing my subscript there, times c3. If I plug a into the fourth derivative, I'm going to be left with just this constant term, 4 times 3 times 2 times c4, which is 4 factorial c4. And so now what we're seeing is this pattern where whatever derivative I have taken of my function here, when I plug a into that, I get that number factorial times c with that subscript. So for example, the fourth derivative of f, when I plug an a in, gives me 4 factorial times c4. And so we can see that this pattern would continue indefinitely if I just kept plugging in, or if I kept taking more and more derivatives. So to generalize, I get to the nth derivative of f, evaluated at a, is equal to n factorial times cn. And if you remember, our goal here in the original power series was to figure out what each one of these coefficients are. Well, if I solve this for Cn, then I have a formula that will give me the nth coefficient for whatever value of n that I want to plug in here. It's equal to the nth derivative of f evaluated at a over n factorial. That allows me to find all of those coefficients, which allows me to determine exactly what that power series looks like. So we have a theorem kind of summarizing these results. If f has a power series representation at a, which is to say that f of x is equal to some power series of this form, and if we have a positive radius of convergence for that power series, then the coefficients of that power series are given by this formula. Again, the nth coefficient, where the very first one is we think of as the 0th coefficient, is equal to the nth derivative of f at a over n factorial. And when n is equal to 0, we interpret the 0th derivative of f as if you had never taken any derivatives, and that would just be the same thing as f of x. Okay? So this is kind of the fundamental result that we're going to use throughout this section. So kind of plugging those coefficients and writing the power series out long ways, our power series would look like this. F of x is equal to f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial x minus a squared plus and so on and so forth. You can see how the pattern applies. Now, you can do this at any value of a that you choose to center that power series at, assuming that your function is 1, infinitely differentiable, because you need that to be the case to get all of these derivatives, and 2, if all of those derivatives are have a in the domain of that function. So you can do this. So Any series that takes this form is what we call a Taylor series of f, centered at or about a. We use either of those terms right there. The Taylor series, the thing to keep in mind, we're introducing a new terminology, but it's not actually a brand new concept. The Taylor series of a function is just a power series representation of that function, but we call it a Taylor series when we kind of evaluate it using this technique here. It is very common to choose a to be equal to 0. So in other words, to find a Taylor series for a function centered at 0, because it gives us kind of a simpler looking power series. It occurs so often that we give a special name to those. So if a power series or a Taylor series for some function f of x is centered at 0, this is what the power series would look like, and we call this a Maclaurin series for f. So a Maclaurin series is not a different thing from a Taylor series. It's a special case of a Taylor series. It's when it's centered at 0 specifically. Okay? So one thing that needs to be pointed out here, if we go back to the very beginning, the very first sentence in this section, suppose a function f of x can be represented by the power series below. That's an assumption that we're making. So right off the bat, we're assuming that f of x has a power series representation. If that assumption is true, then this is what that power series would look like. But that's not always true. There are examples of functions for which you actually can find a Taylor series. So in other words, you can find infinitely many derivatives for that function and find a power series like this, but the function itself is not necessarily equal to that power series. So again, the f of x is only equal to this if we already know that f is equal to a power series at all. And we'll talk about how to determine that a little bit later, but we have to keep that in mind. When functions are equal to their Taylor series, then we refer to those functions as analytic. Now, that's not a term we're going to use much in this class. I'm telling you what the definition of it here, but we probably won't even mention it again. That term comes up again in other classes. You'll talk about analytic functions in a course on differential equations, for example, that comes up. Or a whole lot, that term comes up in a more advanced class called complex analysis. But we're just mentioning it here because it's relevant to what we're talking about. Okay. Another really important fact to keep in mind is that power series representations for functions are unique. So what that means is that it's impossible to have a function that's equal to two power series which have different coefficients. So for example, if I found a power series for some function f of x, which, maybe I found it this way. I found it by evaluating its Maclaurin series, maybe this one right down here. There is no other set of coefficients that I could swap any of these out for so that the resulting power series still equals that f of x. The reason that's important is because now that we've introduced Taylor series, we've now found more than one way of determining a power series representation for a function. What this result means is that if you find a power series representation using some other method, say like what we did in 11.9, then there's no need to then go and find its Taylor series, because its Taylor series would give you the exact same coefficients. So we're going to, keep that in the back of our minds as we're going through all of this stuff. So we're at our first example now. I want to find the Maclaurin series for f of x equals e to the x, as well as its radius of convergence. So this one says Maclaurin series, which specifically means this one. We're evaluating f and all of its derivatives at 0 when we're finding these coefficients here. Okay, so e to the x is typically the first function you find a Maclaurin series for, because it's the easiest one. If you notice what's needed to come up with this Maclaurin series, you need to find all of the derivatives of this function. Now, of course, I can't list out infinitely many derivatives, so typically you're working out the first few derivatives and looking for some kind of a pattern. because then that pattern you can generalize and find, kind of the general nth term of that Taylor series. So e to the x is its own derivative, which by extension means that any number of derivatives that I take of this function will always give me e to the x. So I can generalize that just by saying the nth derivative of f at x is equal to e to the x, right? No matter how many derivatives that I take. So that implies that if I plug 0 in, because that's what we're doing for Maclaurin series, we're plugging 0 into each of these derivatives, I have e to the 0, which is equal to 1. So now, how do I write the Maclaurin series for this function? Well, I can say that e to the x is equal to the sum from n equals 0 to infinity, and this is what our Maclaurin series looks like. But we just showed that fn of the nth derivative of f at 0 is equal to 1 for every value of n. So that numerator becomes a 1, and then I have over n factorial times x to the n. And typically we just put the x to the n up here. If I were to write out the first few terms of this thing, it would look like 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. Okay, that's the power series representation, or the Maclaurin series for e to the x, centered at 0. Maclaurin series are always centered at 0. There was another part to this question. We needed to find the radius of convergence for this power series, and we can do that like we've done before by using the ratio test. So if I take the n plus 1th term of this function, or of this expression here for these terms, and I take the limit as n goes to infinity of the absolute value of that n plus 1th term, so that's x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. Notice that x to the n plus 1 over x to the n is just x. I keep the absolute value, but I can pull that out of my limit. Okay, what I'm going to be left with after simplifying this is n factorial over n plus 1 factorial, which I don't need absolute values for because that would be positive no matter what. We know how this simplifies. I get the absolute value of x times the limit as n goes to infinity. This will cancel with all but the n plus 1 down there. All right, now regardless of what x is, no matter how big, this denominator here is going to go to infinity, which takes this thing to 0. So regardless of how big my absolute value of x is, it's going to be multiplied to 0 because that's what this limit is. So I get 0, which is, of course, less than 1. So by our ratio test, this converges regardless of what x is equal to. That means that my radius of convergence is infinity. And remember, what that means is that this power series converges for all real numbers. Okay, so that's good to know. That's very useful. We've got one Maclaurin series down. We're going to do more, but before we do that, a little bit more background that we need to go over. So what we did over there is we found the Maclaurin series for the exponential function e to the x. But if you recall, we talked about this. It's possible that a function is not equal to its Taylor series. It's possible that we can compute the Taylor series, but if that function was not actually equal to a power series at all, then the Taylor series is just a thing that we derive that doesn't necessarily have any importance to that function. So what we need to be able to show is that that a function actually is equal to its Taylor series somehow. Okay, so to do that, we're going to define the nth partial sum of some Taylor series of a function f centered at a as what we call the nth degree Taylor polynomial. So basically that's when we take a Taylor series and we cut it off somewhere, so we're only looking at a partial sum. So this is the notation we use, capital N with a subscript of n. That's Tn, or the nth degree Taylor polynomial. It's defined to be this. Notice that this sum goes to n instead of infinity. So our series is no longer a series. It's just a polynomial, an nth degree polynomial. Now, as we've seen in previous sections, sometimes we want to approximate the sum of a series using a partial sum. And we oftentimes want to know how good our approximation is by thinking about a remainder term. So remember, the remainder term sort of represents how far off your partial sum is from the actual sum of that series. And we can define it this way. The nth Rn, which represents the remainder of the nth degree Taylor polynomial, is equal to f of x minus Tn, this partial sum right here. So it's whatever would be left that you cut off from that series. So if you're able to show that that remainder term goes to 0 as n goes to infinity, then we would have this. The limit as n goes to infinity of your nth degree Taylor polynomial by solving this for Tn is the same thing as the limit as n goes to infinity of f of x minus Rn of x. This f of x here has no dependence on n, so it doesn't need the limit at all. It's just f of x minus the limit as n goes to infinity of Rn of x, which we assumed this limit goes to 0 here. That would leave you with just f of x. But of course, this limit as n goes to infinity of this nth degree Taylor polynomial is literally just the Taylor series. So in this case, we have that the Taylor series is equal to the function f of x. Okay, so that leads to this theorem, which tells us what we want to do if we're trying to figure out whether a Taylor series is actually equal to the function that it represents or not. The goal is to show that the limit as n goes to infinity of your remainder term is equal to 0. If that's the case, then your function is equal to its Taylor series on that, with that radius of convergence, on that interval of convergence there. Okay, now, how do you actually do that? Well, as we've seen before in previous sections where we deal with the remainder, you oftentimes can't figure out what that remainder looks like explicitly. Typically, you have to find some upper bound for it. And you want that upper bound to get smaller and smaller as n gets bigger and bigger. So it would be helpful if we could find a way of bounding that Rn there. And that leads to this thing here that we call Taylor's inequality. So I'm going to state this inequality, but then on the next video, we're going to walk through a proof of it. So here's what Taylor's inequality says. If the n plus 1th derivative of your function at x, so yeah, the n plus 1th derivative of f of x, in absolute value is less than or equal to some number m, capital M there, anytime x is in this interval. So x minus a is less than or equal to d. Okay, and if you remember, this interval right here, just for reference, is the same thing as a minus d, a plus d. That's what that interval is. So notice it's centered at a, and it goes d units to the left of a, d units to the right of a. Then the remainder of the Taylor series satisfies this inequality right here. So the absolute value of my remainder is less than or equal to that m that we've cited right here over n plus 1 factorial times the absolute value of x minus a to the power of n plus 1 for all values of x within this interval, which remember is the same thing as this interval. This inequality has kind of a lot going on in it, and the proof is a little bit involved. So we're going to use the next video to talk through that, and then we'll look at some examples of how we're going to use Taylor's inequality.